lines about.
Yes. What's the largest number? So that's the problem here is every year I tell them to install this Express thing so I could do things in Mozilla, and then it disappears again over the summer. So I've given up. I'll just show you the code. And you have to trust me that it runs. So it just starts with the usual model. What you do is you can do things like in the declarations, you can say n equals 7, which makes a constant n, and that can't change. So if I started changing n somewhere below, it would be an error. Then you have to say the thing that you want numbers to be a variable. Now, what kind of variable? Well, actually, it's called type. So what type of variable will be an array? Okay. The elements in the array will be integer numbers. And the boxes, the individual boxes, will be called 1, 2, 3, 4, all the way up to 7. Well, whatever n is, but in this case, 7. And then you want a variable which is called largest, and it's just one integer number, so it's not an array. Okay? And that's what you say in the declarations. Oh, I want my variables to be this. Okay? And then this is like an assignment. Right? So this double colon here, it plays the role of the colon equal, but this is the one that's used for arrays. Okay? So you say my numbers, that's going to be an array, and the first element is 22, the second one is 13, and so on, and the last one is the 7th is 31. So this is what you do, and then this is the actual. I'm looking for the largest number. So this is slightly dubious. I will come back to it. This says, okay, so this starts the actual loop. So the loop goes between this do and this end do. This is like in MATLAB, you have the end at the end of the loop. Okay. And every time, so I takes the values between 1 and n. So I is another variable. Okay. Well, I didn't say I wanted I to be a variable, but maybe I could. Here I could say I want I to be an integer. Well, I don't have to, because if I start using a variable which I didn't say I want, that's usually fine. Well, it's only fine if it's an integer or a real number or a true-false variable or something like that. If I wanted to start using an array without saying first, I want this to be an array, that would be an error. But that, okay, don't have to. So even the largest wouldn't have to be there, and this I doesn't have to be there, but it can be. Okay? And what it does is, first it sets I to 1. And then it looks at the numbers sub I, so numbers sub 1. So that's the first element in the array numbers. It's 22. And if that's larger than the largest I found so far, then it replaces the largest. And otherwise it does nothing. And it goes on, and it looks at the second number. So this is exactly the thing that you probably did in your mind when you were looking at first number, second number, third number. Just remember the largest one you've seen so far. And if a larger one came, you replace it. This is exactly what that code does there. Okay. And the dubious thing is the -1. So is this going to work? In this case, it's going to work. But the problem is, if my numbers were only negative numbers, then it wouldn't work. Right? So this code, as it is, it works under the assumption that the numbers that I'm getting in the array are non-negative. If I put only negative numbers, then the -1 would always stay largest. That's not what you want. Okay? So but I'm not going to fix it now. This was just a, this was anyway just a distraction. Any questions about the distraction? No? Good. So we do something else. Oh, so this is, I think, what you have in the on the sheet. Have you read it yet? Okay. What is the question? What is the problem? We're trying to solve. Okay, you've got so this is the thing, right? You want to solve the problem, but you don't know what the problem is. So I asked, what is the question? But in fact, what is a better question than what is the question? A better question is, what is the answer? And of course, I don't. Of course, the answer shouldn't be specific at this point. But what is the answer going to be? To describe the answer rather than give the numbers, right? So the answer here is going to be, also you should eat this much of chocolate fudge cake and this much of chocolate ice cream and this much of this and this much of that every day or whatever. Yeah, every day. Okay. So if you want to understand what the problem is or what the question is, it's good to think of what the answer is going to be, even though you don't know the numbers in the answer, but this is going to be what you're giving Arthur to eat. Okay? This immediately then leads to the decision variables, because you know what quantities you want to give to Arthur, so you have to have a decision variable for each of them. Okay? So that's the kind of thinking that you need to have. So is the question, is it clear now what the problem is? Roughly? No. So what is the method how we're going to arrive at how much of which food Arthur should eat? Method is linear programming. But linear programming solves everything. Every life problem can be solved. So first, let's summarize what we know. So what we know is that there is a certain set of all foods. And also for each food from the set, we know the calories, and we know the chocolate content, and we know the sugar content, and we know the fat content, and we know the cholesterol. and you know the price. Okay? A good start is to summarize what we know. What are the three parts of any linear programming formulation? No? Yes, exactly. Decision variables, objective and constraint. You think of decision variables first because without them you can't write the rest. You don't know what the decision variables are, you can't write the objective. The objective contains the decision variables. Without decision variables, there is an objective and no constraint. And I said what the decision variables were going to be because you want to know how much of each of the foods Arthur should eat. So these are the decision variables. That's what you want to know. You want to know is the decision variable. We know is, okay. So what we want to know is the amount of food F eaten by Arthur against day, and then there's one for each of the two. Okay? Seems clear? What is the objective? Minimize, agree. So I can't write it. Did you say minimize P? What's P? Oh, but which price? The total price. And you're heading in the right direction. So, okay, so minimize, and I'll put it as big P, and this is a small P. There's one always clear in my handwriting, which is the total price that you pay. And so, what is the total price you pay in terms of the letters that are populating this area of the page? Okay, so as an example, if we eat 2 pizzas, what's the price going to be? And this is from 2 centuries ago, because the pizza for £1.30 is probably. Given this table, I have to update the numbers. So if you eat 2 pizzas per day, for example, and nothing else, how much are you going to pay? 260, right? If you eat X pizzas, how much are you going to pay? 130 times X pizza. And if you're eating different foods, then you have to add them all together. Make sense? Okay, so adding them all together is that symbol. Multiplying the price of one food by the number of foods that you're eating is this product. And you have to say where the index F comes from. The index F goes through all the food, to multiply the price of the food by the amount of the food, and add them all together. Okay? So that's negative. What are the constraints? Doesn't show there anymore, but it shows there. How do I? At least 3,600 calories, for example. Is that a constraint? So what does it look like as a formula? Not the same as that formula over there. So when you add all the calories, all the food times by the amount of the food eaten, that gives you the total calories, and that has to be at least 3,000. Okay, then you also want at least 6 ounces of chocolate. And this should also make it metric. So this is a constraint which says that you look at the chocolate content and times it by the amount of food eaten, add them all together, that must be at least 6. So, okay? And that will be a couple more. But I'm not going to write because now everybody knows what they are. And what else is going to be there? Yes. So each of the XX so what's the answer? How much of what to eat? Have you solved it yet? Isn't your homework problem? So when you turn over, which I can't do because people are still writing, at some point I will do it. Oh, I can do it here. Look. This is getting very complicated. Okay, it gives you almost a complete solution. The only problem is that there are no constraints and objectives. So that's what you have to write here. And another tricky thing about it is that all these numbers that are in the table, which you can't see, I've put into an Excel spreadsheet. And this bit between 14 and 22, what it does is it opens that Excel spreadsheet and it reads the numbers in it and puts them into arrays within those. It's quite fancy. So that's something very nice too. Okay, so that's the homework. Any questions about this this problem, exercise, whatever you want to call it? What is it good for example? No? No questions? Shall we do one more? Maybe two. Two more will do too much. Oh, that's wrong. So much linear programming at once. Okay. So there are two problems in the handout and in the slides. One is production of alloys, and the other one is bicycles. Who wants the first one? Who wants the bicycles? Who wants to go home? That didn't win any votes, so we have to do the bicycles. Okay, let's do the bicycles then. Sorry if you've been reading the alloys. We'll do them next week. Oh, but the bicycles are very interesting. Okay, the problem with the bicycle is the following. You're producing bicycles, okay? And you know that in January, you're going to sell 30,000 of them. And in February, you're going to sell 15,000 of them, and so on. And that's the numbers in the table, okay? So that you know. Now, what you also know is that you have 2,000 bicycles at the moment, which is the beginning of January. Okay, we should have solved it at the beginning of January. And you know that your factory can produce up to 30,000 bicycles, and if you ask your workers to work overtime, they can produce up to an additional 6,000 bicycles, so 36. Okay. Now, however, you want to satisfy everybody who wants to buy a bicycle. So, because in June, July, and August, people will want to buy more than 36,000, you will have to produce something in advance, perhaps in winter, and then store it, and then sell it in the summer. Okay? But there are some costs related to storing the bicycles, namely, think that it costs you £5 per bicycle that you're storing at the end of the month. Okay? So this is the kind of accounting. They're only very roughly saying how much it's going to cost you, because you're not saying, you're not looking at whether it's there for 2 weeks, but you just say, well, if it's left over at the end of the month, then we think it's £5. So you're going to get an approximate solution, but it'll be good enough. Okay, that's now. So what is the answer going to be? It doesn't ask any question, does it? But what do you reckon the question should be, or what should the answer be? Come on. Yeah.
Satisfies the demand. It doesn't do many sort of storage.
Yes. So the answer will say how many bicycles to produce every month. Okay. And what you were saying is you shouldn't be storing too many. So that kind of wants you to minimize the cost overall, which is okay. So first, what do we know? So we know that there are 12 months to do the planning for, so I'm going to call them 1, 12. Instead of month like this, it's called the time horizon. So when you're planning ahead in time, period that you're planning for, follow the time horizon. That's common terms. What else do we know? We know the demand in every month. So we know the M is how many bicycles we need to sell. What else do we know? Current stock. So current stock, for some reason I'll call it I0. We know the maximum production capacity. So this is 30,000. And we also know the maximum production in overtime. So and that is 6,000. Next thing it tells us is the production cost. So I'll call it C and C dash is the production cost. In regular time and in overtime. Last thing is the storage cost. Okay, so I can look a little stuff here. C is 32 and C dash 40. S is 5 pounds. Okay, now we know what we know. Now the problem is what we want to know. That's the decision area. Or is there anything else that we know from the bracket? What are the decision variables? Okay. Number of bicycles produced each month. Yes. Okay. So I'll call it xn. Okay. Any other decision variables that you would like? Yes. Oh, yes, you would. So what you want is separate decision variable for the number of bicycles that are produced in normal time and a decision variable for the number of bicycles produced in overtime. Okay, you could probably get away with not splitting it into two decision variables, but it would be quite a complex task to write the right objective and constraints then. So it's much easier to write, take another variable and this will be the number of bicycles produced in overtime. That's a very good observation. Any other decision variables that you would like? Yes. Yeah, you typically would, yes. So another decision variable, well, it's actually each of them is not just one, but each of them is 12 because for every month that's one. So it's like you could say an array of decision variables. So you want one for inventory. So this is the number of bicycles goes in inventory at the end of the month. What we know is now that. We don't know anything. Okay. What is the objective then? It doesn't say, does it? What do you propose? No? Exactly. So usually you want to minimize profit, but sometimes there is no profit. So yeah, so it's to minimize cost. Okay, but of course you need a formula in terms of the decision variables and the things we know for the costs. So to this end, you need to know what your costs are. So what costs are mentioned in the text? Many? The two. Well, two or three, depending on how you take it. What are they? Yeah. Mm-hmm. So that's quite simple, right? So production cost is C for each bicycle. The number of bicycles made is XN. In the C dash, these are the ones that are produced in overtime. And then there's storage, which we call S. And that's multiplied by that the cost.
So that makes it seem like it's a little bit.
Yes, because you don't know what M is. Yes, the sum of all of these. Is it like that? I didn't. Oh, you want another sum here? And another sum here? Could do. But I'm too lazy, so I'm just going to put that into that does the same trick. So without the brackets, the sum only applies to the first term over here. So you need the brackets to make it work. Okay, that's the objective. Now the constraint. I know where I have my constraints, so I'll have to. Okay, so what kind of constraints can you see? Production capacity, is that a constraint? Yes. The production capacity you run, what you produce is no more than the maximum in a month. And you should say what M is. So this is a constraint, and there's one for each month, like that. So for all M in M. So this is my favorite trick. I use 3 or 4 of the same letter. And they're all different. There's a little n, which is for the number of months, which is here. There's big N, which is for the maximum production per month. And there's this curly n, which is for the set of all months. And that should also be a Gothic n. Okay, there's also one like that, which says that in overtime we can't do more than limit on overtime. that everything? Who thinks that's everything? You think that's everything, or do you want to give me anyone? Who thinks there are more? But if there are more, what are they? You have a suggestion? Okay. Okay, suggestion. So what you produce in total to be at least the demand. Is that what you want? And you want this for all the months. Okay, so can anybody see the problem with that? Oh, you have to account for the bicycles. Sorry. And now I wrote it in a silly way, I can't fix it. Okay, so what you have is not just what you produced in that particular month, which is xn plus xn. What you have is you produce, and also what you have in storage from the previous month. That's the total that is there to cover the demand. Right? Yes? I am. No, sorry, what's the current stock? Oh. Good thinking. That will answer itself in a couple of seconds, well, a minute. So yeah, keep that question in your mind. We'll come to that. If I don't say anything, then remind me. Okay? Okay, so in a certain month, what you have is what you've produced, plus what you've produced in overtime, plus what you kept from the previous month. Now you want this to be greater than or equal to the demand, is that right? But then how do you know how much you're storing at the end of the month? What you really want is this to be equal to the demand plus what you store away. Now you get a constraint, which what it does is, it looks at all the bicycles I have available in this month, coming from production, and coming from overtime production, and coming from storage from the end. And now, and on the other side, it looks at, what am I doing with them? Okay, I'm selling some, and I'm storing the rest. And in that constraint, there you want equality, because it's exactly what it is. That nothing gets created anywhere, and nothing gets lost anywhere. Exactly what I have is what I use it for. Okay, and that's the constraint. So this one is a good working version, but the other one is better. So how about the I naught? Okay, so here n is a set of months, and at the beginning, I said that the set of months start with 1. So n is 1, 2, 3, 4, 12. Okay, so this constraint, where do I write? So n is 1 in the first month. This means what I produce in the first month, plus what I produce in the first month and over time, but the initial bicycles in storage is what I sell in January, but what I store at the end of January. Okay? This is where I not come into play. But it's a bit of a cheat because I1 and I2 and all the way to I12 are decision variables, whereas I naught is not. That's part of the data, part of what we know. What we'll find with that. Mosel is not. There will be trouble. There will be trouble. But so far for us, for the mathematical formulation, before we get into that trouble, for us it's any other constraints? The usual ones. Yeah? Not manipulative. Xn dash In should be greater than or equal to 0. So why does this make the demand satisfied? Like it doesn't seem to. Well, that's a question that I usually get from students. So why does it make it? So in fact, what makes the demand satisfied is that you're requiring the amount in storage to be non-negative. If you didn't, you could store a negative number of bicycles. That would mean that in that particular month, you didn't have enough for everything to sell to everyone. Then you have negative, but we don't allow that. So let's make sure that everybody buys the bicycles they want. Whether there is a feasible solution or not with these numbers, that's a different question. But in the model, if you get your optimal solution, that's going to make sure that the demand is satisfied. Okay, any more questions? Not too many, because I'm getting exhausted. Yeah? Do you have a question? No? Look like it's going to happen. Well, maybe it's going to check. I think it's fine. That's a symbol for end of formulation. I made it up. That's my symbol for end of formulation. Yeah, so what we're doing in general at this time is looking at various problems that look like something nasty, and then we'll produce something that we know what to do with, kind of know what to do with, and then the next thing we do with these formulations, once we have them, once we've listed the constraints nicely and neatly as a mathematical constraints, and you know what you're doing, you can then go on the computer and write the code that actually solves it. Okay? That's the general idea of what we're trying to learn. And the way we're learning it, because there is no fixed way of doing these things, is that we're looking at various examples and trying to learn as much the technique as possible. So the particular things that we learned today was one of this kind of continuity constraint. Okay. This is similar to the pipes we had in the gummy berry juice. Whatever comes in has to get out. So whatever comes in is the bicycles we produce and we take from storage. What we're putting it is selling it and putting it in storage again. The idea is the same as with pipes. And what else did we learn? Not much, because I got carried away with the race. But yeah, that's okay. And you have an exercise that you can solve in this. Anything else you need? Well then, have a good evening. See you later.